Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuit, and today we are discussing the manufacturing technique of the MEMS. Now microelectromechanical systems. So in the MEMS we have discussed the deep reactive ion etching. Now we discuss the deep reactive ion etching of the glass. So we take the glass substrate which can be used and which can be etched deep into the material with the high aspect ratio, and this technology has been gaining a popularity in the MEMS fabrication. So a structure fabricated into the glass using this technique will be done, and then SAN images has been taken. So the typical etch rate for the high aspect ratio etching range between the 250 to the 500 nanometer per minute. So depending on the depth of the photoresist metal or the polysilicon can be used as a mask. So what type of mask we are using depend upon the deep etching ratio of the deep etching. So SAM of the high aspect ratio structure etched into a glass substrate fabricated by the MNX. Now you see that this is the 125 micrometer deep etch in the quartz. So you see this is a 120 micrometer. So deep etching, and the structure you are seeing like a pillar, and this is the SAM image of the deep etching on the glass substrate. Now another type of method is the manufacturing technique is the hot embossing method, a process to replicate deep high aspect ratio structure into a polymer material is to fabricate the metal tool insert in by using the LIGA or a comparable technology, and then to emboss the tool insert pattern into a polymer substrate which is then used as a part. This process explains that replica will be done by using this hot embossing. In the hot embossing, a tool is prepared that is put into the polymer substrate, and after that this tool is used again and again. So when we are doing the deep high aspect ratio, so we prepare a tool in the form of the polymer substrate, and then this pattern is used for the embossing. This embossing, in this embossing, a hot embossing process will be done because the tool is heated and that is embossed in the polymer substrate. So a mold insert is made using a appropriate fabrication method and having the inverse pattern made into it, so that the inverse pattern, because we are preparing so that the same pattern we can get, because we will put into the polymer. So the exact pattern we will get if we prepare the inverse pattern in the mold. So the mold insert is placed into a hot embossing system, and that includes a chamber in which a vacuum can be drawn. Is the substrate and the polymer are heated to above the glass transition temperature, that is the TG of the polymer material, and the mold insert is pressed into the polymer substrate. This embossing can be done only in the polymer. So the vacuum is critical for the polymer to faithfully replicate the feature in the mold insert, since air would be trapped between these two surfaces, resulting in distorted features. Subsequently, the substrates are cooled to below the glass transition temperature of a polymer material, and force is applied to de-emboss the structure. So as a result, whole hot embossing can successfully replicate complicated deep and high aspect ratio features we can get by using this hot embossing. This process can make imprints into a polymer hundreds of the micron deep with a very good dimensional control. You see on the screen, this is the process. You see the black part is the mold and the below part is the wafer. This is the plastic substrate, heat plastic substrate, and the mold insert to above plastic temperature, that is the TG, pull vacuum on a chamber. Another figure shows that apply the force to emboss plastic substrate. Now you see, as embossing has been taken place, now the last, now the module will be the mold will be removed from this plastic substrate. Now this plastic substrate will be cooled down and the pressure was inserted so that it cannot be deformed. So the cool plastic substrate and the mold insert to demolding temperature and apply force to de-emboss. So a particular structure we can get as per requirement. So these are 3 steps in the embossing. First, heat the plastic substrate, then a mold is put on it, insert the mold on it. Second, apply the force to emboss the plastic substrate so that the pattern can be imprint on the plastic. After that, cool the plastic substrate and the mold insert to the demolding temperature. It will be removed from the substrate and then apply a force to de-emboss. So the advantages of this process is that the cost of the individual polymer parts can be very low. It is compared to the same structure made using the another technology. It means we can prepare a replica. We are having an imprint, we can use this imprint many times. Because of the overwhelming cost advantages combined with very good performances, this polymer molding process is very popular for producing the microfluidic component for the medical application, and this mold can be further used in the another manufacturing techniques. Heat plastic substrate and the mold insert to above the plastic temperature, pull vacuum on the chamber, applying the force to emboss plastic substrate, cool plastic substrate and then mold insert to demolding temperature and applying force to the de-emboss. This is a very simple process and that will be used. Now you see the SAM image of a small test structures made in the plastic substrate using the hot embossing technology, and the height of the plastic microstructure is nearly 300 micrometer, and the smallest feature have a diameter of about the 25 micrometer, and that is has taken by CNRI. Other micromachining techniques, in addition to the bulk micromachining, surface micromachining, high aspect ratio micromachining technologies, there are the number of other techniques used to fabricate the MEMS devices. So MEMS devices, so now we have the XEF2 tri-phase etching. This is the xenon difluoride, that is XEF2 in a vapor state is an isotropic etchant for the silicon. Means we can use xenon difluoride as an etchant for the silicon. So this etchant is highly selective with the respect to the other materials commonly used in the microelectronic fabrication, including like LPCVD, silicon nitride, thermal SiO2, aluminum, titanium and the others. So it is a one of the etchant is a completely dry release process. It does not suffer from the stickiness problems of the wet release process. So this etchant is popular with the micromachining of the microstructure in the pre-processed CMOS wafer, where the openings in the passivation layers on the surface of the substrates are made to expose the silicon for etching. Another method is the electro discharge micro matching. This electro discharge micro machining or the micro EDM is a process that is a EDM. Why it is EDM? Because the electro discharge micro machining, and this process used to machine a conductive material using the electrical breakdown discharge to remove the material. So, working electrode is made from a metal material onto which high voltage pulses are applied. So, next this working electrode is brought into the close proximity to a material to be machined, which is immersed in a dielectric fluid. So, the minimum sized features that can be made with micro EDM are dependent on the size of the working electrode and how it is fixed, but holes as small as tens of microns have been made using this method. So, one of the issue of this micro EDM is that it is a slow serial process. Another type of micro machining is the laser micro machining. Lasers can generate an intense amount of the energy in very short pulses of the light and direct that energy onto a selected region of the material for micro machining. Like we can make a pattern by using this laser micro machining. Among many types of the lasers, most of the lasers used in micro machining are CO2, YAG, excimer, that also use H has its own unique properties and capabilities suited to particularly applications. So, we can do etching by using the laser. So, these lasers can be used for the laser micro machining. Factors that determine the type of the laser to use for a particular application, that including the laser wavelength which we are using, what material we are using, which wavelength laser we require for the etching. Next, what is the energy of the laser, power of the laser, and the temporal and the spatial mode of the laser, means what we are doing in the form according to the time domain, according to the surface domain. So, we choose the laser in such a manner. The material type which we are using, features, size, means tolerance, size, sometimes the power is more, the damage of the material takes place. So, the power and the tolerance, processing speed and the cost, all the parameters keeping in mind, then the laser micro machining has been done. The action of CO2 and an ND arc laser is essentially a thermal process. So, whereas the focusing optics are used to direct predetermined energy, power, as well as the density of the well-defined locations on the workpiece to melt and vaporize the material. Another mechanism, which is the non-thermal and referred to as a photoablation, occurs with the organic materials and it uses the ultraviolet radiation, and for that the excimer, harmonic YAG laser, as well as the other UV sources are used. Similarly to micro EDM, laser micro machining can produce the features on the order of the 10 of the microns, but it is the serial process and therefore the slow process. Next type of micro machining is the focused ion beam micro machining, that is the FIB. This is a versatile tool for performing the micro machining, and that is a focused ion beam. The accelerating voltages are adjustable from a few kilo electron volt to the several hundred kilo electron volt. The spot sizes can be focused down to below the 25 nanometer, making it capable for producing the extremely small structure. You can see the size of the beam is very narrow, and that beam can produce a extremely small structure in the nanometer size. So, when we are preparing a very thin, very small devices in the nanometer, then we use the focused ion beam micro machining, and the user can input the 3D CAD solid model of desired etching topology can be used. It is a computer control stage with the sub-micron positional accuracy allows very precise registration of the sample. Means we require the computer control stage for preparing for using this micro machining, because we are using a controlled development of a devices. In addition to material removal, FIB can also be used to perform ion induced deposition, lithography, implantation doping, mask repair, device repair, and the device diagnostics that can also be done by focused ion beam micromachining. Many of these tools can also be outfitted with a secondary column for mass analysis of particles removed from the substrates using the USIM. You see, this type of machining we use for the focused ion beam micromachining. This is the one type of machine. Now, the another part which is very important is the scaling law in miniaturization. As we are preparing the MEMS and the microsystem design and manufacturing, the important parameter is the scaling. Because scaling, we are preparing a very thin, a small devices. So, in this era of the think small, one would intuitively simply scale down the size of all components to a device to make it small. Unfortunately, the reality does not work out the way. So, for this, as we are preparing a very small devices of the nano size, so scaling is very important in the miniaturization. So, we discuss the some of the scaling tools, some of the scaling parameters in the miniaturization that is used in the MEMS devices. And it is true that nothing is there to stop one from downsizing the device component to make the device smaller, as the devices are making smaller and smaller nowadays. So, there is a requirement of preparation of miniaturization of the devices. So, in this miniaturization of the devices, the properties should be similar, the property should as per requirement, the output should be as per requirement, input should be requirement. So, there are however the serious physical consequences of the scaling down many physical quantities. So, keeping all the physical quantity intact, the scaling of the devices will be done in such a manner so that it can be performed better as it is going to be smaller and smaller. So, the scaling laws that will make engineers aware of both positive and negative physical consequences of scaling down machines and devices. So, there are many parameters of the scaling. We see that on the screen that scaling in the geometry is also important, scaling in the rigid body dynamics is important in the MEMS devices, scaling in the electrostatic forces, scaling in the electromagnetic forces, scaling in the electricity, scaling in the fluid mechanics, scaling in the heat transfer. So, all these, because the MEMS are used in every field, so the every parameter should be accordingly to the requirement. So, all these scalings are very important when we are discussing the MEMS manufacturing. So, why scaling laws are important? Miniaturizing machines and the physical system is an ongoing efforts in the human civilization, and this efforts has been intensified in the recent years as the market demands intelligent, robust, multifunctional, low cost consumer products has becomes more strong than ever. So, the only solution to produce these consumer products is to package many components into the product, making it necessary to miniaturize each individual components. When we prepare each individual component in a small size, then we keep it into the another device. So, miniaturization of the physical system is a lot more than just the scaling down the device components in the size. So, some physical systems either cannot be scaled down favorably or cannot be scaled down at all. So, scaling law thus become the very first thing that any engineer would do in the design of the MEMS and micro system. So, in this lecture we will discuss the scaling, what are the scaling laws that must be important in the development of the MEMS devices, of the nano size, of the micro size. So, scaling law thus become the very first thing that any engineer would do in the design of MEMS and the micro system. So, two types of scaling law we use. Number one, scaling in the geometry, and second is the scaling of the phenomenological behavior. Now, scaling in the geometry, we have the scaling of the physical size of the object. In the another, we just discussed the scaling of both the size and the material characterization. So, whenever we develop the MEMS devices, we keep these two scaling laws in mind. One is the scaling in the geometry, and second is the scaling of the size and the material characterization. These two are used. We will discuss further about these scaling and how the geometry are important in the development or the manufacturing or the fabrication of the MEMS devices, that we will further discuss in the further lecture. Thank you very much.